Einführungsvorlesung zur Inaugural Lecture von Gottfried Mandlburger. Willkommen den Leuten hier. Es sind gerade ein bisschen weniger als 100 oder circa 100 und genauso viel auch im virtuellen Raum. Der Videokonferenz auch noch einmal 100. Das ist sehr schön. Und hier treffen sich zwei Gesellschaften. Zum einen einmal die TU Wien und zum anderen die Österreichische Gesellschaft für Vermessung und Geoinformation, TU Wien. Ich freue mich, sehr viele Kollegen und speziell auch Studierende, da sind sie, da oben, zu sehen und Kollegen von anderen Fakultäten natürlich auch. Und zum anderen natürlich auch viele frühere Kollegen oder Mitglieder der Gesellschaft für Vermessung und Geoinformation. Ja, warum halte ich jetzt da die Einführungsvorlesung vielleicht? Nicht Einführungsvorlesung. Warum halte ich die Eröffnung? Weil ich in beiden Kreisen irgendwie ein bisschen vertreten bin. Einerseits auf der TU Wien und im Senat und andererseits auch in der Gesellschaft im Board. And so we have two short welcome addresses. The first will be given by our rector, and the second will be given by the President of the Austrian Society of Surveying and Geoinformation. So please, Mr. Schneider, the floor is yours.
Welcome everybody to TU Wien this afternoon. I'm really pleased that I can give a small welcome address for this occasion of an inaugural lecture, because I think these inaugural lectures are of extreme importance. I'm really happy that you have the tradition here in the faculty, because I think inaugural lectures have a very important role in just showing to the society, for example, this specific society, what you do, and also to our students in the end. And I already outed myself yesterday in the evaluation process. I'm a fan of Geodesy, because I think it's such an interesting topic that I'm also looking forward to what you're going to present today. I was thinking, what are the links to our new strategy? We have a new strategy since 2 days, and this is brand new. And I see some links to what you do, and also link to you as a person. First of all, our vision for the next 10 years, we developed this in a very participative process. Our vision says, TU Wien, where we dare to reason. I think that's what you dare to reason. Sometimes you have to be really, you really need to dare something and to reason based on data that you have, and to have methods and concepts to base your scientific thoughts on data. And for example, these nice graphs that you're going to show is something that absolutely fits to our vision already. So I think you're already part of it. And it also says that we want to develop into a creative urban tech university. And I think creativity is also much needed in what you do, although sometimes it's underestimated in society that our jobs are creative jobs. Typically, people that come from natural science and engineering science are not seen to be the creative guys. Typically, this is more associated to arts and culture maybe, but my experience as an engineer, I'm a civil engineer, is that what we do is extremely creative, and also we are not able, unfortunately, we are not able to communicate this more to society, and that's also why we think it's important to put the word creative here. And the urbanity to be in Vienna speaks for itself. I think we are not in the nicest building that TU Wien has, I have to admit that. So it's very functional, maybe, yeah, we can put it this way. Still serves for many years, but I still think it has a certain, how do you say that in English, a charm, yeah. It's a specific surrounding that also already gives something that is associated to TU Wien, especially when I talk to people in society, they say that. So it's nice to have it here. I think it's good to have it here. And of course, Tech University is the next one, Creative Urban Tech University. I think Tech University, that's our DNA. We stand for technology, and we need technology. We need society, and we need technology, merge them together. And I think things that you will do will be at the forefront of also the question that comes with all the water issues. first, when I saw your topic, bathymetry, I was a little bit not so clear at the first glance what it is really. I still remember when we had the negotiations, but soon it became clear to me that this is really important topic, especially related to all the water issues. If you go to the mountains now, I was on the weekend, and you see the dry ground there, and it's really something we have to deal with. Where is the water and why and at what level? And that's what I see what you're doing. And finally, our vision says unlimited potential, unlimited human thoughts, unlimited potentials that you will have as a scientist. And I think it already contributes also what you do to our goals, our strategic goals. One of it is that we want to foster scientific leadership and the international the international recognition of TU Wien. And I think that fortunately the faculty here is internationally very well recognized. At least that's what I hear. That's not only what they say, but I also hear that from other sources. And I think the scientific leadership in this field is related to many things that you will present now. I think this is really something where we can make a difference as TU Wien. And I'm really proud that this is part of our DNA, this geoinformation and geodesy. Of course, what we need more is all of you to advertise what we're doing, because typically there is a lack of talented students coming in this field. There is something that will be related more maybe to the data science. There's a new potential of recruiting, but I would like all of you being present today also to talk more about the potential and the very creative works that Professor Mandlburger does, because in the end, only if we spread the word about what you do here and what we do at TU Wien, we can have the talented people coming here worldwide to support all these works. So I'm really looking forward to your talk. I'm curious what you will present to us. And I hope that you, as a young talent, still young, yeah, compared to me at least, yeah, will also continue your way at TU Wien and spread the word in the scientific community, but also do so many things that you do for teaching, because that's the last I want to say. He is really into teaching, and the Jupyter notebooks he prepares are one of the most important things. I inscribed this last semester to be part of it, but I only followed the first lecture. Then I unfortunately didn't have enough time anymore. Yeah, it was too hard. It's too hard because my job is more superficial than yours. Yeah. Maybe you have to give me a personal support to get through it. But please continue your hard work also in the teaching, because it's as important as all your research. Thank you.
Thank you very much. Sehr geehrter Herr Rektor, lieber Professor Gottfried Mandlburger, liebe Festgäste. Lebenslanges Lernen zu fördern ist eigentlich das Hauptanliegen unserer österreichischen Gesellschaft für Vermessung und Geoinformation. Wie machen wir das? Wir publizieren die Zeitschrift für Vermessung und Geoinformation 4-mal im Jahr. Wir organisieren den OVG Summit, vormals bekannt unter Geodetentag, alle 3 Jahre. Und wir veranstalten, so wie hier heute, OVG Vortragsreihen. Und es ist mir deshalb eine große Freude, zusammen mit der TU Wien heute die Antrittsvorlesung von dir, lieber Gottfried, veranstalten zu dürfen. Denn wer könnte lebenslanges Lernen besser verkörpern als du? Die Neugierde und die Leidenschaft, mit der du an dein wissenschaftliches Arbeiten herangehst, ist sofort greifbar, wenn man mit dir zusammenarbeitet. Und ich hatte das große Glück, ein gutes Jahr mit dir das Büro zu teilen. Und ich blicke wirklich sehr gerne auf diese Zeit zurück. Darüber hinaus schaffst du es auch, deine Leidenschaft für Geodesy und Geoinformation an die Studierenden weiterzugeben. Und das ist aufgrund deiner wirklich herausragenden didaktischen Fähigkeiten. Und du bist damit ein Wissensvermittler im besten Sinne des Wortes. Abschließend möchte ich mich noch bei der großen Zuschaueranzahl bedanken. Weiters bedanken bei meinem Organisationsteam hier für die Vortragsreihe in Wien, bei der Alexandra und beim Lothar. Und ich freue mich auf eine spannende und unterhaltsame Antrittsvorlesung von dir, lieber Gottfried. Bitte.
to start with, I'm overwhelmed. It's a real pleasure to have an overfull lecture hall. This is what you would love to have also on a weekly basis. So that's basically my dining room, so to say, my living room on a weekly basis. And I also appreciate that we have a couple of, as I heard, participants from the online forum. 100, and I will also want to give you a warm welcome. So I want to start with optical bathymetry is the topic of today's talk, right? Here we are. And I want to start with a short, let's say, overview of my career, my academic career. I studied geodesy here in the university at the TU Wien. Had my master's back in 1995. Then I was 1 year in private industry before I came back to the then Institute of Photogrammetry and Remote Sensing, where I first worked as a software engineer. So we do have an in-house software production, and I was mainly working on this side before I switched over to research. And this then resulted in my PhD in 2006. Which was already related to hydro. So it was related to hydrology and hydraulics, but it was not in optical hydrography or optical bathymetry. It was rather using traditional sensors like topographic laser scanning images and combining them with SONAR, with sound navigation and ranging. And I had then the opportunity to work here, continue my work as a postdoc, and then the optical hydrography thing started basically with laser scanning, with laser bathymetry. It was a point in time when instruments got so high resolution that it made sense to apply it to Austrian waters, and that's then inland waters, whereas it was firstly rather a matter of coastal mapping with larger footprints and so on. Along the line, then I was 3 years in Stuttgart between 2017 and 2020 at the Institute for Photogrammetry there, and this gave me a lot of opportunity to and freedom to research and also to publish. And this then resulted when I was back 2020 at TU Wien to finish my habilitation. And after a successful application for a professorship in Innsbruck, I was very happy to receive a counter offer here from TU Wien. And this was then accompanied with a fast tenure track procedure. So with the normal procedure, assistant professor, associate professor. I'm now happy to have this full professorship since last year and this inaugural lecture on optical bathymetry, and that is the talk today, optical bathymetry, optical hydrography. I won't make any difference between bathymetry and hydrography. Bathymetry both comes from the Greek. Bathy means depth, hydro means water, and the graphene is the mapping part of it. So it all has to do with water. We are mapping underwater, and either we are interested in the depth or we are interested in the whole thing, the whole water body. And that's why I termed it today optical hydrography rather than optical bathymetry. What I want to speak in the next 50 minutes, something like that, is divided into mainly 3 parts. The first one is introducing the discipline as such, right? So giving you the basics. This is the lecture part of it. It is an inaugural lecture, right? So you are now my students for the first part. And then I want to look back to the last, let's say, 10 or 15 years. So what did we do in research in the field of optical bathymetry so far? And this will lead me then to the current situation. So where are we today and what are our topics today? And this will then be the chance to introduce my PhD students, which I'm very happy to work with and to present basically their work. And then I will want to wrap up the thing with what is this all good for? We have also a mission at TU Wien, so technology for people, I think it is, Technik für Menschen. And that's basically it. So I'm very happy that I got the impression that what we do is also adopted from society. It is really for humanity. It is for society. And I will give you some examples on that. So to prepare the ground, it is first probably good to have a look at the different water depths which we do have worldwide, right? And this starts with the deep ocean area down to 11,000 meters. And then we have the coastal areas here in the middle. And then we have the very shallow areas. And there are the optical methods. They are only capable to deliver products in the shallow area. So wherever light can penetrate, that's the crucial thing. That's where the optical also comes into play. We can measure, right? And now this is only a very small part of the waters which we do have, the shallow water, but it is a very important part because wherever light comes in, there is also life, light and life that goes well together. Whereas for other areas which are also important, like the deep sea and the nearshore area, we need other techniques. So the omnipotent measurement strategy is SONAR, sound navigation and ranging. You know this from every boat has a sonar on it, and if it gets very deep, then we are to geophysical gravimetry-based methods. The optical methods here, we employ them either with the sensors above the water level. That's basically my field of expertise. And we do this either from satellites or from aircraft or from helicopters or from unmanned area vehicles, so to say drones. But of course, we can also mount the sensors, the optical sensors like cameras or laser scanners underwater. We can mount it on a ship, on the belly of a ship. We can equip a scuba diver with an equipment. Of course, it needs to be waterproof then. And in the recent past, we also see, let's say, trends that it is that we see underwater robotly operated vehicles, so to say, ROVs, which are equipped with cameras and laser scanners, and also purely automated carrier platforms, right? But we will mainly concentrate on the above water thing. So speaking about optical bathymetry, I think we can say that there are three methods coming from active or passive domain. So active and passive, what does this mean in the first place? Active means we create the light which we measure our own, that's basically lasers. And on the other hand side, we use the light which is there, which basically comes from the sun, right? And in the second part, we can divide to, well, that's basically then making an image, making a photo. And what is on the photo? We see colors on the photo. So that's the radiometric content. That's the first thing where we can measure with. And the second one is we see texture, we see objects in photos. And that's where the photogrammetry, the hardcore photogrammetry comes into play. And I start my round two with the spectral bathymetry. Just need to find my mouse. Here it is. And I have at least one. I don't have many slides, but that's a slide formula. That's one which is so important. And David Lusenga, one of the big names in the community, did a very good job in condensing everything into this very, very easy and simple formula, but still physically reliable and physically meaningful. What basically the concept is, and that's what you see on the image, we have brighter and more darker tones. We have green. You see this here on the map of Austria, right? So we have these greenish tones, and you have a notion that there it could be shallow, right? And then it is getting more bluish and more darker, and then this would be probably the deeper part. And let's say in mathematical terms, this means that we have three components. The one is the LS. This is the reflection from the water surface. I put it very simple. It's really the reflection, and there's much more in this LS. I could talk an hour only about the LS. Believe me, I won't do it. And on the other hand side, we have then the second term, which is the product of LB. This is basically the brightness of the bottom, B for bottom. So consider you have a bright sand, and it is very, very bright, and or consider you have mud or seagrass, and it will be dark, right? And then whatever is in the water is in the last term, and that's the most important one, and it says e to the power of minus something. So we do have an exponential decay, and what is in the exponent? In the exponent, we have two terms. One is h, this is the water depth. So we have increasing attenuation within the water, the deeper we get. And then we have the alpha, and the alpha is a measure of, let's say, turbidity. It's the attenuation coefficient. And again, this is one of the parameters which we could talk hours for. The pretty thing on this is you can just take the logarithm, and then you have the h, the water depth on the left side, and everything else on the other hand side. So it's really possible with a single image to measure water depth, right? In the community, of course, it is much more complicated or much more sophisticated, I would say. We have to deal with sun glint. Sun glint is the direct exposure of sunlight into your field of view of your image. You very much like this with your holiday photos when you have the sunset and you have the sun and then the mirroring of the sun on the ocean. That's where you like it, but we hate it if we have it for mapping, believe me. And then, of course, we don't take one band, but we have these multispectral instruments now, traditional cameras with RGB, red, green, and blue, but on satellite, we have many more bands which we can use. This is the first, on the last slide, we had a physical interpretation. How it is done, let's say, practically is more a regression problem. And what do we need for this? We need first the radiometric content. This could be an orthophoto. This orthophoto stems from the Federal Office Mapping Agency of Gyro, so thanks to them. And then we need ground truth. So we need some certain points where we do have depths. And in this case, they are coming from a SONAR, from an echo sounding mission. And this was provided by another cooperation partner from the University of Innsbruck, the hydraulic department there. And then you can draw a nice graph where you have the radiometric content on the x-axis and the depth on the y-axis. And hopefully there is a functional relationship, as it is in our case with the parabola. And then we can feed the function, then can we apply the function. And for each and every pixel, out of a sudden, then we get a depth. We will get a real depth map. You outed yourself, Mr. Rector, that you're a fan of cartography specifically. I hope that you specifically like these drawings then. But what we do here in Geodesy is we are always interested in how accurate is it. So we can compare it to reference data. And in this case, this is a mountain lake, so Blaue Lacke, Blue Lake in the Zillertal area. And we were able to achieve an accuracy of 60 centimeters, which comes to 5%. So 5% is something which you can reach with this radiometric methods. So if we don't use the radiometry, but the geometry, then we are to photogrammetry. And specifically, we are to multimedia photogrammetry. I'm very happy that the foundations of multimedia photogrammetry, namely the two media photogrammetry, air and water, was established in Austria by Karl Rinner, unfortunately not at TU Wien. He was a teacher in Berlin and in Graz, but there's a nice connection to OVG. That's the seminal paper for optical multimedia photogrammetry, and that was published in the VGI. Yeah? So that's very nice. Of course, this is now going into really not only the two media case, but the multimedia case. So what is our setup? That shows me at the Pilach River. We will hear about the Pilach River more in the talk. And that's the traditional, let's say, photogrammetric setup. We have the very same scene with overlapping areas, and we are able to identify, like in this case, also submerged, a boulder, right? So you see this boulder on different areas in the image, and from these image observations, we should be able to derive a 3D position. So from 2D image positions, a 3D position in our object space. So that is how it would look like. We need to know where the cameras are and how they are oriented. And then we identify one at a homologous point, so the orange one here, and then we can forward intersect it and we get the 3D position. But in water, it is more complicated. We have to consider ray refraction at the water surface, at the ray interface. And the physics behind it, maths behind it, is Snell's law of refraction, which you know from school, right? So it's not that's not the tricky part of it. But still, you need to keep it in mind and consider it. If I was in class now, then I would go through a numerical example like this. This is a UEV set up with a water depth of 3.2 meter, apparent water depth. And then I would go through all the formula. And why is there this bluish thing here?
One participant and we don't find an option.
So it's not my fault, right? Okay, no.
The participant does not find a way to.
Okay. No. I don't worry about it. But I spoiled now my own joke, or not a joke, but the fundamentals. So we have 3.2 meters as the apparent depth, and the real depth would be rather 4.6 meters. So there's something like 1.3 multiplication factor in between, to put it short. And then I would show them a real world example from a river section. That's from an image matching algorithm, and we see here the parts on the dry ground and also the submerged parts. And I would draw then a cross section in the middle of it. And what is striking here is we don't see the water surface. Where's the water, right? If we look from up down, to the in nadir direction, then we don't see the water surface on the images, right? So the first thing is we have to how to get to the water surface. And that's where we often do very simple things. We use the land-water boundary and so on, and the simplified models like horizontal water surface models. And that's part of the problem which we are facing today in research, right? And the rest is then, if we have the water surface, the rest is, let's say, pure maths, and it's not too complicated. But we need to apply it, as you can see, the raw and the corrected version here. The next thing is then, if we switch from passive to active, then we are with laser scanning. So how does laser scanning, specifically laser bathymetry, works? We send out from any airborne platform, could be a drone, could be an aircraft, could be a helicopter. Mounted on it is a scanner. We send out a laser pulse. The laser pulse travels through the air and first hits the water surface. On the water surface, a signal gets reflected. Part of the signal gets reflected. And as water acts like a mirror, pretty much of the energy is going back, going away from the sensor, right? So it's direct reflection load, so to say. If you're lucky, part of it goes back to the sensor. What comes next with green light is that it also penetrates into the water surface, into the water column. And that's where the attenuation starts. That's the e to the power of minus something. Remember back on Lysenko's formula, right? And the attenuation is a sum of absorption, so pure signal absorption in water, which is much higher than it is in air, and scattering. So we have particles in the water, and on all particles, scattering takes place. Now I've already talked about we need the water surface for the refraction correction. That's why the bathymetric laser scanners often also use an infrared laser source, a red infrared laser source, which does not penetrate into the water surface, but gives us a direct reflection of the water surface. And that's the pure reason for using it, because we need to know the water surface. From the green part, that's the very typical signal waveform. I will speak about waves in two contexts. The one is we send out a pulse which looks like a wave, and we get something back which again looks like a wave. But this is the signal, which and every time when I say signal, a full waveform, then I mean the signal, other than the real wave, like the wavy water surface as you would have, right? So in this case, this is the waveform, the full waveform of our backscattered signal, and it is composed of first echo, a first peak from the water surface, then this exponential decay. Remember back to the Lysenko formula, and then we have the second echo from the ground. So that's what the textbook says. And for laser bathymetry, the same applies as we had it for the photogrammetry part, only that the raw measurements in this case are too shallow. And why is this? Again, it's a consequence of Snell's law, because not only the refractive index is into play, but also the propagation speed. So that light is simply slower in water, much slower in water than it is in air. And then I would again present an example, and that's what the difference is. In laser scanning, we see here on the left-hand part, blue points, there are certain reflections from the water surface, but they are not continuous. You see this more clearly here in this cross-section, right? But still we have to model the water surface, and you see we only have a couple of points which give us the real water surface, and the rest needs to be reasoned. Right? We dare to reason. That's the vision of TU Wien, right? And then comes the simpler part. That's again Snell's law and the application of it. Lecture closed, so to say. Yeah. Now we are in what did we do in research in the past 10 or 15 years? And following the principle of what we do here, what we are very strong here at the research area of photogrammetry is knowing what the sensor does. We are not electrical engineers, but we're geodesists. But I think we know quite much about how the sensor works and how they are oriented. And that was the first part of my work, so to go into these different systems which we have. And one of the questions which you always have if you speak to people is, how deep can your laser penetrate? And the answer to this is, it's very relative. It depends on mainly what the alpha in Lysenko's formula is. So the turbidity, right? So the more turbid it is, the less we can penetrate, the more clear it is, the better we can penetrate. And an empirical measure for that is the so-called Secchi depth. Secchi is an Italian hydrographer of the late 19th century, I think, and he invented a disc of a 20 centimeter size, and you lower it down in the water, and the point in time where it cannot see is the so-called Secchi depth. That's an empirical measure for turbidity, yeah? And you can see this here in the ground. And in the laser bathymetry, we see two different instruments, the deep water systems, which use high pulse energy, and they are implemented with long laser pulses and broad pulses, so not good in spatial resolution. And then we have the counter thing, so to say, the counter concept, which is the shallow water systems, which using very shallow, very short pulses. To speak about short pulses, we don't have only scientific people here. We are speaking about nanoseconds, yeah? Nanoseconds. So we have milli, you all know what milli is. So it's the thousands of a meter is a millimeter. If you divide the millimeter through 1,000, then it's micron. That's what we do in photogrammetry. The image coordinates, we measure them in micrometers, so thousands of a millimeter. And if we divide the micron into 1,000, then you're at the nano level, right? And if you do this in the temporal domain with the seconds, then you can think that it's a very, very short time. Is nanosecond, yeah? And the deep systems use 10 nanoseconds and the shallow systems use 1 nanosecond. 1 nanosecond for the speed of light is very, very speedy. So to say with 300,000 km per second, 1 nanosecond means 30 centimeters in the metric domain, right? So just that you have an idea. What I wanted to say is that we do have systems which are only using shallow, deep channels like FUDRO, red system. Then we have a couple of sensors from Hexagon, from Teledyne Optic, which use both. And then we have also some instruments which only use these shallow channels. And one of these is the family line VQ800 from Regal Laser Measurement Systems, a constant cooperation partner of ours and a world-leading manufacturer, which is based in Austria. And I'm very happy to see many faces of Regal today in the audience. And this brings me to one of our achievements in the last 10 years was to create an open data set, an open lab, I would say, an outdoor lab at the Pilach River. The Pilach is located in the eastern of Austria. It's a pre-alpine river. The specific test site here is near to the confluence of the river with the Danube, near Melk. That's where we are, let's say, playing. That's where our scientific playground is. And our standard flight clock, which was first flown in 2013, consists of 3 flight lines in the cross direction and 4 flight lines in the longitudinal direction. In this one, we have an additional 5th one at 100 meters lower than the other longitudinal flight lines. And the basic things on the river, the Pilach River, is in between. And the good thing is, and you see it on this, let's say, 3D visualization, it's very diverse, right? So we have residential area. We have agricultural area, we have forests, we have normal forests, we have littoral forests, so forests near the river. Then we have the river itself, and then we also have ponds, a couple of ponds. And they are of specific advantage for us because they are the remainings of open pit minings, by the way. So that's the foundation of the motorway A1 near in this area. And what remains was a freshwater pond, right? And depending on the usage of it, if there are fish in, if there are plants in, they are more turbid or more clear. And this is specifically useful for us because we have a very, very short domain, very different properties of water bodies. And we were able to trace down the evolution on the technological sensor side with a paper which we produced in 2023 for an ISPRS Congress, conference, where we took out one of the turbid ponds so that the depth here, the visual depth is only 1 meter, 1.2 meters, something like that, so really turbid water. And with the classical way of handling the full waveform for the signals, which is not storing the waveform, but doing it in the instrument online waveform processing. Again, we have a cartographic representation here with a depth map. So you see the depths in different shades of blue. And you see there is an area which is very pale. So we have our doubts that it is full penetration here. Yeah? And we will see, yes, if we introduce more sophisticated waveform processings like exponential decomposition, by the way, this was a doctoral thesis here at our institute by Roland Schwarz. I'm very happy that you're here today. I'm supervised by Norbert Pfeifer. which is a specific way of handling the waveforms. I put this short. And with this specific technique, we were able to penetrate much deeper, right? And then on top of that, we had another idea of what if we integrate multiple waveforms in the vicinity, so we do averaging, then we got deeper and deeper, and for something which 10 years ago was impossible to penetrate down to the bottom, we were now able, as you can see in this cross section, so that's the cross section, which is shown on top here. And we see on the left-hand side with the standard online thing that many of the blue points are here in the middle between the bottom and the surface, and only with the, let's say, averaged, exponentially decomposed version, we get down to the ground of 4 meters in a very turbid pond. So that's the advantage on this side. This side. And the second, let's say, focus point was then this meander loop. We captured this with various aircraft, so this with an aircraft, fixed wing aircraft. I have a small video for that. You see the opening here on the right top border. So that's the opening of the circle where the instrument looks down. And we had a video camera here. You see the ponds, the different ponds. On the right hand side, you see the meandering river. So that's really a seldom case that we have such meandering rivers. Normally our rivers are straight, right? And then we have this specific meander loop, which is one of our focus points. We also did this with helicopters, and we did this in the last time also with miniaturized sensors of the box of a shoebox with drones. I'm very happy that also David Monetti is here from Skyability, a service provider who is running this system here. That's a Regal laser scanner VQ840, and the drone is from Skyability. So there's a video on that. So let's take off with the drone on this steep cliff here. There we have mind that the back current here, so the water is going back in the tilt of the river. And if I'm able to stop it probably here or here, then we see all the problems which we have, or all the opportunities or challenges. We have rippled water surfaces, we have sandlint, and we have on the top left, very clean and smooth water surface on the ponds, right? So everything in one place. And that's part of our problem, to be able to reconstruct the water surface for the further processing. First things which we did was, of course, fluvial morphology is one of the big things. You have a flood event like it was in 2014, and we had a pre and a post event data evaluation or data capture, and we calculated the digital terrain models, which you see in graded in shades of gray here, and superimposed we have the differences. So this is basically the movement of the sediment, and in blue tones we see the deposition, and in red tones we see the erosion. So parts of the up to 50 centimeters and more, right? So really large packages of sediment were decomposed and were moved from one side to the other, with a total of 20,000 square meters. To put you in the right position, this is 2,000 truckloads. So you need 2,000 trucks in order to restore the situation as it was beforehand, right? Yes, and that's the point in time where we use this very valuable data set also in teaching for our bachelor and master thesis. So we have a strong belief in combining teaching and research, so in research-oriented teaching, and that specifically is possible with the bachelor thesis. And one of the outstanding bachelor theses we had, this is basically not from Geodesy, but from environmental engineering. I see a couple of environmental engineering students here, whom I teach in the 5th semester and the 6th semester. We have the bachelor thesis. And it was Carolina Damm, and her topic was to find the Talweg. The Talweg is the lowest lying point of a river, and the connection of all lowest lying points. So it's a way of a river axis, right? And what Carolina did is she stripped the vegetation from the ground, and then she fitted a curve through all the ground points in a section. That's basically the red one here. And then she also did this for another point in time. That's the blue one. And then she evaluated it. and calculated that from the spline curves, which were resulting the lowest altitude, the lowest point, and connected all them. And then this results in two different curves, the red one in 2014 and the green one in 2021 it was. And the striking thing is we have an axis shift of more than 40 meters, although the Pila River is only 20 meters wide. So it's twice the width of the river, which was caused by one flood event in 2014. That was the point in time, and I'm happy that Kuhn just arrived from delivering his children from the kindergarten, collecting them, because this was a jointly supervised PhD with Kuhn. Kuhn is from the hydrology department. He's a professor of hydraulic engineering, and I asked him to co-supervise the thesis. And his statement was, yes, that's fine with the targets, but they are not so interesting. What would be interesting would be the complexity of a profile. Is it only one channel? Do we have two channels? Do we have a braided river systems? And that was what Florian did in his story. What did I do now? What Florian did in his bachelor, Fabian did in his bachelor thesis. He followed up on the work from Carolina and extended it to the, let's say, more complex domain. Another topic and another important topic is AI, artificial intelligence. And where this comes into play for us is specifically in the context of semantic labeling, classification. When we have a data acquisition, like in the laser, we get points, but we don't know to which class these points, initially, we don't know to which class these points belong. And that's one of the tricky parts to say, this is a ground point, this is a point on the water surface, this is a point on the water bottom. And that's where AI is specifically powerful. And we were able to build up on a PhD, which was also supervised by Norbert. And we have Nan Li here, who is now with Regal Laser Measurement System. By her time at our institute, she laid the foundation for this deep learning-based classification. And this was then in the joint bachelor thesis evaluated for the complex case of bathymetry. And where lies the complexity? We have overlaying layers with water surface, and below we have the water column, and even below that we have the water bottom. And that's of course a bit tricky to delineate this. And deep learning was surprisingly good at doing this. And then one last bachelor thesis, which I want to bring before in front of the curtain, is that the work of Nike Wagner. That was now not on the Pila test site, but it was on Lake Constance. One of the big issues is we have a massive change in underwater vegetation due to climate transition. So the water is getting warmer. We have invasive species, and that's pretty a problem for all our alpine lakes. And there was a demand from the University of Hohenheim, that's the BOKU from Stuttgart, and Klaus Schmieder joined us or showed up and asked us, could you give us a classification of the bathymetric laser point cloud, which we do have, into something which is meaningful for us as ecologists. And this was basically the task of Nike to divide it into low-growing, high-growing, and very high-growing vegetation. And he was surprisingly successful with that. So we have here the map, where you can see the red spots, they grow to the water surface. The dark green, that's the large plants, and the light greens are the, let's say, grass-like vegetation, right? And this was surprisingly successful. We even managed to publish a paper out of that in remote sensing. This sounds as if we would only do laser scanning. That's not the case. We are also doing multimedia photogrammetry. Again, we are back at the Villach test site. And you already know this. And what I want to show here is this is a refraction corrected final product which we derived. Pretty much of this we did with our in-house Opal software. So we have also members of our team here in the group. And what I want to stress here is the difference in performance between airborne laser bathymetry and airborne imaging with respect to bathymetry. And this is the result, two sections, 1.5 meter deep, the one, and 3.5 meter deep, the other, the lower one, with the respective areas here in green, or the points in green, from multimedia photogrammetry. And what we can see is we can penetrate very nicely here in the shallow area, like here. my mouse. Where is it? You can't see my pointer, can you? Oh yes, you can. Here in this shallow area, it's very, very good, but the deeper it gets, the more, let's say, fuzzy it gets, right? And the reason for that is that we are not able to estimate the water surface correctly. That's our main limiting factor, and that's still an ongoing problem. Again, I'm back with, let's say, charting. So that's the digital terrain model derived from the laser and superimposed now with the depth map from the laser. So that's smooth but sharp on the other hand side, and that's the depth map as derived from the photos. So it's more salt and pepper style. So we are not as accurate in the shallow domain, yes, but in the deep domain, no. And the question is now, how can we do better? And I also already gave you, let's say, the hint. The main reason why we can't do better so far is it is very hard to get a grip on the water surface. And that's what we are basically doing today. And that brings me into the position that I can introduce four or five of our PhD topics. One from Lauren, which is a FWF funded, so basic research funded project named Photogrammetry Wave. This is exactly on this find the water surface topic. It's a joint project together with TU Dresden, with Hans-Gerd Maas, group from Hans-Gerd Maas. Then we have a second basic research project also funded by FWF, named Bathymetry. This goes into the direction of artificial intelligence, neural radiance field. So that's this 3D reconstruction with artificial intelligence. It's run by Markus Bretowski. We're just in the very beginning with this project. And then we have two industry funded PhDs under my supervision by Michael Grömer from Verbund. So hydropower, the hydropower inspection is here the big topic. And then one in laser bathymetry from Jan Romberg-Kauert, and this one is sponsored by or funded by Riegel. And the thing here is to push the limits with laser bathymetry. And we are always helped by another PhD, which is not specifically bathy-oriented, by Lukas Dammert. He's our, let's say, Trumpfass, as you would say in German, Jolly Joker, and he helps us in pretty every project. And before I go into the project, I just want to well, what you do is, if you have a problem, or what we do is often we make a data collection with as possible, as defined conditions as possible. And this was the case, what we did after this devastating flood event, which we had last year in September. All the Austrians remember, back we had this devastating flood event. And then we went back to our river, Billach River test site, so that's the meander loop, which you already know. And I'm very happy that I yesterday received the information that our article, which we wrote, and this was a joint paper of all the contributing TU Dresden, Karlsruhe Institute of Technology, University of Innsbruck, and of course headed by our group at TU Wien. And we did not only write the article, but we also published the data set open. So we are dedicated to open science in terms of whatever we write should be readable by others. So that's open access publications, but we want to also make the data sets which we work on open. And there we did this with the research, how is it called? Research data infrastructure from TU Wien. So in this case, both the article and the data are published. And that's just an impression from our measurement campaign. We had many, well, 4 or 5 drones from different sizes, from this large to that small. We had us as the pilots, that's me and Lauren, and Silvia Klaas from University of Innsbruck running 2 of these DJI M350 drones. And this is some results which we had one on the one hand side from the images, and on the other hand side from the laser. That does not help if you don't have proper reference. And that's where Lucas also comes into play. He helped us very much with a very rigorous reference network. We had ground control points for the photogrammetry, and we even weighted the river for having ground truth in the underwater area. And what Lauren did, and that was our first idea in the project Photogrammetry Wave, is to make a snapshot of a situation with a wavy water surface, right? So one way of dealing with wavy water surface, because the water always changes if it is dynamic, is to have simultaneous acquisition of photographs. And we first tried it out in a lab. We have in the Gusshausstraße together cooperation with our engineering geodesy, a black tank, and we had a system with 4 synchronized cameras, all cabled. 2 of which in the rear ground here are looking obliquely to the tank, and you can see some texture on the water surface, right? So we are hoping that we were able to reconstruct the water surface from the specular reflections on the water surface. And then we have the standard, let's say, nadir images where we look through the water surface to the bottom, and that's 2 different situations. But to be honest, we were at the beginning very discouraged because we did not get any reasonable high points on the water surface with classical methods. And then we switched over to AI-based methods like superpoint, superglue, light glue, and all of a sudden we at least are able to get features on the wavy water surface and also to get matches to corresponding features on it. That's what matters at the end of the day. And we were encouraged by that and went out in the October campaign and had this 2, let's say, synchronized images, but that was manual synchronization. But still, we were able to see that there might be a chance. And Laurent did a test, and the blue points are now our matches, and they are pretty reasonable within 10 centimeters of our smooth water surface. They might even be more correct than the smooth water surface is, by the way, right? So this is now a world a premiere. So with this in mind, we investigated is it possible to have 2 drones without a cable connection, triggering 2 images within 1 millisecond time interval discrepance. And that was work which was done by Martin Wieser, a colleague of mine. He's very good in this, let's say, electronical things. And this is our this is Sony camera, and that's our GPS box. We use the PPS pulse from GPS to synchronize the triggering of the camera, and that's the first image which the colleagues took yesterday. A completely different approach would be to mitigate the effect of the water surface dynamics. And how could you do this? You could do this by taking many pictures of the same scene. So we were just hovering a drone in the air, looking down. And as you see in a single image, we have this submerged targets here, and they are very, very, very blurry. And why are they blurry? They are blurry because of the shape of the irregular shape of the water surface. That's the reason for the blurriness, right? But if you take 100 photos and you merge them, you co-register them and then merge them, it's surprisingly, look at the difference here in sharpness on this image, on this features which you get there. And that's the point where we stand. We don't have let's say quantitative measures, but we're very confident that we can make a step forward in this direction as well. The other thing is AI, and there we're heavily relying on neural radiance fields. So neural radiance fields comes from more from computer vision. So the question is, I have an object, I photograph it from all around, and then am I able to have to produce a photo from a different perspective, where I didn't take a photo from? And that is done with a feed-forward neural network. It's a non-convolutional neural network, which gives us, predicts us the colors, so to say. The problem with bathymetry is that it is not refraction aware. So we need to have this refraction effect at the water surface. So our idea in this respect is to divide it into 2 models, one above the air and the other below the air. So that's our basic aim in this project. But as I said, we are only at the very beginning. But Markus Betzowski provided me this nice rendering, which I want to share with you, where we can see, so there are meaningful results from these neural radiance fields, even impressive results. But I would not show you the point clouds. At least I would not show you the point clouds in the bathymetry because it's complete rubbish. Why? Because it's non-aware of the refraction. So that's where we stand with AI and 3D reconstruction. Then we have Michael Grömer. He is working for Verbund for hydropower, and his topic is monitoring potential damages on dams. And normally what you do is every 10 years, each dam is emptied. And as we had it here in 2023 for the Puck reservoir, the Puck is between Styria and Carinthia, right? And we took the opportunity to do a laser scan of the water side. So what we see here is the water side, right? And we took also total station measurements. We glued targets on it. So that's the targets which we glued on. And then when it was refilled, we were also able to do this with underwater photogrammetry. And how was Michael able to do this? So they have a ROV, a robotly operated vehicle, where there are cameras on. It's a very cheap GoPro camera, by the way, right? And due to the that we have so many control points, we were able to achieve decent accuracy. And that's a rendering which Michael provided for exactly this lecture today, where you can see the results in 3D as an animation. And you can see we have some holes here, so it's not perfect. That's because it's very difficult to navigate underwater with the ROVs. We have some very nice details here and some areas which are not covered. So that's one of our control points, as you can see here. So that's decent results, and we are investigating this further together also with specialists from Italy, who are more in this underwater photogrammetry thing. And then the last topic which I have is the work of Jan. Jan is working in many fields. That's how he is. And one of the things is also trying to see through whitewater. So this was a topic which was brought up by Theresa Himmelsbach. She was a visiting scientist from University of Innsbruck. And she asked, and she's a hydraulic engineer, right? And she's very much interested in these mountain areas and what is going on in the subsurface of the mountain areas. And she was very disappointed that we don't get any points under these whitewater areas here and there. And that's triggered, let's say, the research at our site, and no research without, let's say, reference measurements. And we don't need to go to Tyrol. We also have this at the Pilach River. There is a weir, there's a dam, and this is Jan recklessly standing in the current. I think I also have a video for that, where you can see how strong the current is. And then on the other side, this was photographed by Lucas standing on the total station, right? And the idea behind this was basically a joint idea of Florian. We also have Florian Pöppel here. So Jan and Florian investigated this together. So the thing is that we lack any points here in this area where there's the white water. And the idea is, can't handle this. Yeah? And the idea is first to do this waveform averaging, waveform, not waves on the water surface, but signal, waveforms averaging. And then we get something like what you can see here. It's smooth, and it has not this traditional strictly downgoing. It has a certain peak, but we're not able to detect a peak in this form. But if we would subtract a nominal answer, like we see it here, then we end up with a remaining difference curve, which shows two peaks. And the latter one should be related to the bottom echo. And it was surprisingly good results. As you can see, all the orange points, they are filling the gap with the, well, beforehand did not have any data. In comparison to reference data, while it's in the range of 10 centimeters, it's not as accurate as we would love to have it, but it's still decent results. And this was also made possible by the help of Lucas Dammert, who is our engineering geodesy tie to photogrammetry, so to say. And one of the issues we had is how do we measure ground truth in the current where you can't hold a pole vertically, right? And the answer was using the tracking with two total stations and two prisms. So we tracked the upper and the lower one, and then it doesn't matter if it is tilted or not, you always get the right position on the ground. It was the part Lucas was contributing. So where is this, or what is this all good for? And I'm very happy that I can share a couple of slides only. We're five slides away from the finishing line, so no worries. Coastal protection is one of the things. So in Germany, this is from, where is it? Schleswig-Holstein, so between North Sea and South Sea. North Sea, very turbid water, Secchi depth of 1.5 meters. Even the authority there says, yes, even if we only see 1.5 meter, it is important to run these techniques which we have, 1.5 meter. If we have a sensor which is 2 Secchi depth, then we can penetrate 3 meters. And that's the crucial coastal zone. We see this here on the right-hand side. It's on the North Sea. That's the Wadden Sea. And all of you who know the Wadden Sea, so it's tiny little structures here, which come very nicely here with the laser bathymetry. This was an exceptional thing on the River Elbe in 2018. Probably you remember our summers are getting drier and drier. And once we had this enormous low water, you reported this, Mr. Rector, now coming from your winter holidays that we are lacking water. And this was exactly where we were not able to run boats on the ships on the Danube, if you remember back. But for the bathymetry, it was of course a good thing because we had only very shallow water. And that was where Airborne Hydromapping, a company in Tyrol running a regal laser scanner, by the way, was contracted to measure 600 km of river. 600, let this sink in. So it's not a tiny briefcase as we do it at the Pilach River, but 600 kilometers river mapping with an airborne bathymetric system as the basis for hydraulic and for flood simulations. And this was I'm very happy to also be able to present material from here, from Austria. And one of the driving forces, I'm very happy that you're here, Christian, from the Federal Office of Federal Mapping Agency of Upper Austria. And they are a driving force in systematically surveying rivers for the sake of flood protection, flood risk mitigation. It's still not complete, as you can see, but it is in several hundred kms which they already served, mainly together with, I think David Monetti is also here, Skyability as service provider, and Upper Austria as the driving force. And very nice pictures here with penetrations down in the Traun River, 10 meters. So that's amazing. And all these maps, you can see the residential areas here, the very detailed bathymetry from the laser. Here, very, very prominent details. So that's boulders. That's very important for the hydraulics because it makes roughness, right? That's groins. That's man-made. You can even see that the groins are about to getting demolished. So they are very in shape in this area near to the coastline, the shoreline, and they are in not so good shape towards the middle of the river. And this was also post-disaster after the 2024 flood event. You see this area, this was all river material which was coming with the flood and then was, let's say, poured out into the agricultural area. Yeah. And I'm very happy. Yesterday, I was informed by my wife, actually, did you see this? There's a green laser on ORF News. And that's basically was a data acquisition at the Sil River in Tyrol. And what you see here is a Video 860 instrument from Regal flown from Altadron on a helicopter. And the basic message from this is the pilot project is part of the flood protection in Tyrol. So now I want to conclude here with the message, what we do seems to matter. It is applied by authority. And I want to make a so strong point that it is so important that you do this. You as authorities, you are the first ones to trigger here innovation by just applying it. We had a revolution in topographic mapping at 2000s when laser scanning, topographic laser scanning came into the market. We don't see this transition with the bathymetric thing as severe as it was. It's more an evolution than a revolution, but all the more it is so important that especially the authorities have the courage to apply it, and then of course also our research makes much more sense. And instead of a conclusion, I want to give a round of thanks, and I want to first give my thanks to Directorate, to you, Mr. Schneider, with whom I had my final negotiations, but also to Sabine Seidler, the former rector, who gave me the chance after coming with a successful application from University of Innsbruck to give me this counter offer to stay at TU Wien. And this would not have been possible if there would not have been persons behind advocating for keeping Mr. Mandlburger at TU Wien. And this was basically Norbert. I think you had a major part in this, and also Wolfgang Wagner, Dean of our faculty. So my cordial thanks go to all of you, and I hope that I will be able to, let's say, fulfill what your hopes were in my person. And then my gratitude also goes to the Department of Geodesy. I'm very grateful that Johannes, the head of the team, is here. We have the Dean of Study Affairs here, professors, and of course, so many colleagues. I'm really, it is a privilege working here. So that's my home base. That's a place where it is good to live. It is challenging on an everyday basis. We have this vision of you dare to reason. And every day when I when I open the door, I know that my viewpoints are challenged to the utmost point. We just had today a discussion with this new synchronized system, and Norbert was the first one to question, is this good? But on the other hand, also, what can we use it for? So that's on a daily basis. I think we live this vision already. At least that's how I feel it. I am very grateful to all my students, the classroom students who challenge me on a weekly basis, the PhD bachelor students, Fabian, you're here, many others around who have trust in me for being their supervisor, their mentor, and of course my PhD students. So living with them on ice level is really simply a privilege, I would call it. And then, of course, I had on my very first slide many names, and this was only the names which actively contributed to, which did something, did a slide. But there are so many names which should be mentioned and partners which should be mentioned. And in the very pole position, of course, there's Regal Measurement System. I'm so amazed. I'm so glad that so many people of your company are here today. This really means much to me. And of course, my first of all, thanks go to you, Martin Pfennigbauer, CTO of Regal Laser Measurement Systems. I think we spent very long time in the last 15 years speaking about specific problems in laser bathymetry. And I hope that you also see that it is a win-win situation. It's definitely a win situation for me. I probably would not stand here if there was not this ongoing support from you. And there's also we always have, let's say, research project, not only on a personal level, also on a personal level, but also on an institutional level. We're just discussing a new research project with you. But also skiability, David was already mentioned, AHM, airborne hydromapping, and of course, Upper Austria, Tyrol, all these institutions are so important for me. And then my thanks, of course, go to you, to OVG, and to all the photogrammetric societies where I'm living in, so where I can be, so to say, part of the family. My special thanks go to you, Ali, for promoting this, Lothar for bringing this all up, and for your kind words as a bureau partner, so to say, right? But I also want to mention all these other, like the German Society, the International Society, where I play an active role, and also EuroST are the national mapping agencies of Europe. And of course, last but not least, families, friends. Not all people here are researchers. Many are families or friends. And I'm super grateful that you're with me, that you're interested in me as a person. And before I get over emotional, I switch to a very last slide. What is the next milestone for us? We are organizing in the under the umbrella of ISPRS, the International Society of Photogrammetry and Remote Sensing, a workshop, an international workshop at TU Wien. I'm very happy to be, let's say, the head of the local organizing committee, but many of my team helped me with that. My thanks also go to Felix. Felix is the one who is now organizing the catering outside. And we are expecting 100 participants. We include all the facilities which we have in TU Wien, like the water lab. Thanks, Kuhn, for supporting this idea. It was a crazy idea to go to the water lab. We also included the VR lab. Davis, Doran Goldfarb is included, especially for having things like that. So I have, I'm not that young, Mr. Schneider. I have another 10 years, and I'm happy to serve TU Wien in this 10 years. But, and I'm certainly not bored, and I will stick to airborne platforms, so that the sensor being above air and looking through the open water surface. But probably if I retire, I go for scuba diving. And this is one of the contributions. This will be the kickoff, so stay tuned or even participate at the workshop. And we will bring this. This is not Pixar. This is not Finding Nemo. This is reality. This is 3D measurement. This is 3 years of scuba diving, photogrammetric work. Even if each fish which you see was scanned, was photographed, of course, it's a digital replica, it's a digital twin, but everything which you see here is real, is really geodetic, is mapped, and is not animated in that sense. And with that, I'm at the end. I want to cordially thank you. And I'm open for your questions.